Okay, right. So, as Kirill said, this is the third and final of my lectures. So let's start with a recap. So we're studying this model problem, the simplest possible Helmholtz boundary value problem. Arguably, that's the Helmholtz equation in free space in RD. So recall we're given a compactly supported F. Our task is to find U satisfying this PDE, plus there's this radiation condition that's saying the waves generated by the source F are moving outwards when looked at back in the wave equation picture. And recall we have this a priori bound that in this case you can prove just by integration by parts in this simplest possible case, that the H2 norm of U in any ball of radius R is bounded by some constant times then K times R, the norm F of L2 in this ball of radius R. And remember, I'm waiting. So this H2K, this is a space. In fact, we're going to see again the definition of the space in a minute, where I'm weighting derivatives with inverse powers of K. Okay, because again, in my Helmholtz operator, my derivatives are weighted with inverse powers of K, right? And I'm emphasizing this because we're going to see this derivative weighting with inverse powers of K right on the next slide. And last time I managed to, or I hope I convinced you or showed you that if we can split our solution in this way, that I'm just writing down here in this theorem with this result first due to Mellenkens-Auto in 2010 for this particular Helmholtz problem. So we have this splitting, and that then allows us to prove this really great result about this HP finite element method applied to the Helmholtz equation, namely that it doesn't suffer from this pollution effect. So let's just write down this result that I showed you last time. So it says U restricted to the ball of radius R, where R is arbitrary, but contains the support of F, can be written as the sum of two functions, UH2, plus UA, where UH2, okay, it's in H2, otherwise this would be terrible notation, and it satisfies a bound that's 1 power of KR better than the bound satisfied by the solution U itself. Okay, so there's a compare somehow KR here, no KR here. And then the second part, UA, this is analytic and satisfies these derivative bounds I'm writing down here. And one can show that a function satisfying these derivative bounds is analytic just by bounding the Taylor series remainder. And this function UA then has the same, so let's say UH2, UA, this function UA has the same KR dependence in the bound as the Helmholtz solution itself, but has this advantage, this additional property that it's C infinity and moreover analytic. And this is for all, you give me a K naught and there exist these constants C1, C2, C3 such that these bounds hold for all K greater than or equal to K naught. Right, and last time we saw using this Schatz argument and then these polynomial approximation results, how then this splitting indeed shows that this HP finite element method does not suffer from the pollution effect. Right, so today is the fun lecture. This is my favorite bit, and I'm hoping it's going to be the best bit for you because there's lots of analysis and Fourier transforms and things. We're going to prove this result here. Let me highlight it in here. But before we prove it, I'm going to tell you informally what these functions UH2 and UAR, but I thought I'd first ask the audience if anyone had any idea what, so given U, how do I create, so given U, how do I create UH2 and UA such this splitting holds? So it's okay if there's if no one wants to hazard a guess, but if someone does want to hazard a guess, I want to give you that opportunity. Who's feeling brave? Kirill, are you feeling brave?
I need a bit more time.
That's okay. That's okay.
Hey,
Yes.
It has something to do with I don't know if preconditioner is the right word. It has something to do with taking the principal part of the thing. That's pollution. This might be completely stupid, and I might not know what I'm talking about. But
so it has got a lot to do with the principal symbol of the Helmholtz equation, actually. So you're along the right lines there. So good. So perhaps I'll tell you all what the answer is, but you'll see that this comment from Stephen is actually going to be important in the proof. So thanks. Good. This was a good. Again, I'll pay you the money we arranged. When I see you in person.
All right.
So this UH2 is going to be the components of U with frequency greater than or equal to lambda k for some lambda greater than 1, okay, where I define frequencies via Fourier transform. And this UA is then the components of U with frequencies less than or equal to lambda k. But so we're going to see this in a minute, but just to link this to Stephen's comment, the whole point is that the Helmholtz equation is well behaved on high frequencies. And if you think of this, you're going to think about this principal symbol of the Helmholtz equation. We're going to see in a minute, this is actually invertible on high frequencies. And that's why this UH2, the components with high frequencies, satisfy this bound with 1 power beta k dependence. Okay, so now I'm going to justify that statement to you. Okay. Right, so let's now recap the Fourier transform. Okay, so I'm going to write a lot of things down on this. Everything I'm going to write on this board, you will have undoubtedly seen before, but this is your reward for persevering through this numerical analysis that's perhaps a little bit less familiar to you than the Fourier transform. So I'm going to find the Fourier transform, but I'm going to weight it with k. Okay, so this is just the usual definition of the Fourier transform, but I've stuck this k variable in here, right? You see this k variable, look at here, and so I'm calling them this f sub k. And then okay, let me write down the inverse Fourier transform. Now, so it's just using a change of variables in the Fourier transform. So I have this then k to the d when I do the inverse transform. This is an error here. This is dx here. Right. And why have I done this? Excuse me, sorry. I got something in my eye, I'm getting all emotional talking about the Fourier transform here. So why have I done this scaling? Well, it's because we have this usual rule that the Fourier transform changes derivatives into multiplication by my Fourier variable. But in the Helmholtz world, my derivatives are scaled with this power of k inverse, right? The Helmholtz equation itself has got these derivatives scaled with k inverse in it. So now the advantage of putting this k factor in the Fourier transform is that now minus I k inverse d alpha of phi, the Fourier transform of this is then the Fourier variable psi to the alpha, the Fourier transform of phi, right? So you will have all seen this before without the k, and now I'm putting this k in. Okay, and the rationale again is because Helmholtz equation involves derivatives weighted with K inverse. Okay, so then I'm going to use Plancherel's theorem. See, I used to call it Parseval's theorem, but apparently Parseval is for the Fourier series and Plancherel is for the Fourier transform. So this is something I learned last year. Okay, that's the Plancherel theorem. And then we've got our Sobolev norms, right? Our Sobolev space norms defined, you can define them by the Fourier transform. So let's recall that definition here. So again, this is just the standard definition of the Sobolev spaces HS, but with this K, the K put in, which means then the derivatives are weighted with powers of K inverse. Okay, and this angular bracket is then, so angular bracket of C is 1 plus C squared square root. Okay, so strictly speaking, these Sobolev norms are equivalent up to a constant of the ones I defined in lecture 1, right? Just in lecture 1, I just said you take the weak derivatives, you scale each derivative by power of K inverse. You know, here these are equivalent to those up to some constant, but I'm going to ignore that. Okay. Here are you happy? Are you feeling a warm, fuzzy feeling seeing these facts about Fourier transform?
Am I what? Yeah, warm, fuzzy.
You know, are you feeling good inside? You know, seeing these familiar things about the Fourier transform.
Yes.
Okay, good. Right. So this is all this. These are these facts about the Fourier transform. Now let's define a Fourier multiplier. Okay, and so actually, sorry, I just want to. I'm getting excited to getting ahead of myself. I want to just introduce some notation. Again, very standard. I want to call minus I partial derivative equal to capital D. Okay, because then this is K inverse capital D, and it goes to the psi to the alpha. Okay, so again, this is standard. I hope you've seen this before, or I'm sure you've seen this before. So now I'm going to define a Fourier multiplier. Okay, so this is an operator. I'm going to write A K inverse D acting on some function v of x is defined by, so what do? I take the Fourier transform of v. This is a function of psi. I multiply by a of psi, and then I take the Fourier transform back, right? This is then the psi to x Fourier transform, okay? And then this is a function of x, okay? So I go into Fourier space, I multiply by a, and I Fourier transform back, okay? That's my definition of a Fourier multiplier. And the motivation, right? Well, why am I suddenly studying these? Motivation is that the Helmholtz operator is a Fourier multiplier, P of K inverse D, where this P of psi is psi squared minus 1. Okay, and this notation, calling it K inverse D is precisely because in, under Fourier transform, this K inverse D goes to the Fourier variable psi. Okay, Stephen, are you with me?
Yes, this is easy.
So this is what, sorry?
Yeah, this is good.
Good. Okay. So now I'm going to have then a definition which is slightly non-standard, and I'll make a remark about that at the end. Definition non-standard. We're going to say A is a Fourier symbol of order m a real number if there exists a constant c such that a of c is less than or equal to the constant c, then angular bracket of the Fourier variable psi. This is for all psi. And I'm going to write, well, we'll write then that A is in Fs for Fourier symbol M if it satisfies this growth condition. It's a growth condition at infinity in the psi variable. Okay, so example number one, this P defined here is a Fourier symbol of order 2. Okay, because I've got this psi squared here. Then let's say example number 2, if A of psi is 1, then A is a Fourier symbol of order 0, and you know, and A of K inverse D, this Fourier multiplier, is just the identity, right? Because I go to the Fourier world, okay, I multiply by 1, and I Fourier transform back, right? So I end up with the same function. So then the third example is that if the support of A is compact, then A is a Fourier symbol of order minus n for all n greater than 1. Okay, because I can stick any negative power of psi. So this inequality holds with m as large and negative as I want, just because A has compact support. And then 1 minus A is then a Fourier symbol of order 0. Right, and now I'm gonna write down one lemma about properties, simple properties of these Fourier multipliers, and then we're going to prove the theorem. Right, the theorem, the splitting theorem of our Helmholtz solutions. So lemma, okay, let's say that A is a Fourier symbol of order, say m sub A, and B is a Fourier symbol of order m sub B. So this then implies AB is a Fourier symbol of order MA plus MB, and A K inverse D, B composed with B K inverse D, is just the product AB K inverse D, i.e. the Fourier symbol, so the Fourier multiplier with symbol AB, and which this is then B K inverse D, A K inverse D. Okay, so these Fourier multipliers commute. And finally, this third fact, that A K inverse D maps the space HS weighted with K to HS minus MA with the norm of this Fourier multiplier bounded by this C, which is this constant, in fact here. Okay, so actually so I'm hoping many of you are thinking, my God, why is Ewan writing down these blatantly obvious things? And if you're thinking that, that's great. But I am actually then just going to prove this again. Since it's so simple, we're going to prove this third thing. It's so simple. I'm going to do it in this small piece of board here I have left. So A K inverse D acting on a function V. Okay, the norm of this squared, H S minus MA with K. This is the integral psi angular bracket 2s minus 2ma, then a, then so what is it? It's so this is it's this the correct power of psi. Then we want to put the Fourier transform of the thing that we're taking the norm of. The Fourier transform of this by the definition is then the product a of psi, then the Fourier transform of v. And then I just use my bound on a up here to then say this is less than c, and I then have my psi to the 2s fk of v psi squared, and then this quantity here is precisely the hs norm of v. Okay, so these Fourier symbols then have these nice mapping properties between these weighted spaces. Okay, and in particular here, a is not a function of k. This constant here is not this constant doesn't depend on k, and so this constant here doesn't depend on k. Right, so I have these nice sort of uniform mapping properties between these spaces weighted with k. And it's just because again, just because I built in the k into my definition of my Fourier transform, and then everything else propagates through. Okay, this is it. We're going to prove the theorem, right? Let's just go back and eyeball it again, right? We're going to prove that my solution U, my Helmholtz solution, splits into this UH2 plus UA. UH2 satisfies this better bound, and UA is analytic. So this bound that's better than the bound satisfied by the solution U itself. Okay, let's do it. Okay. This is the proof of the theorem. So I'm going to let chi sub lambda of Fourier variable psi be defined as just the indicator function mod psi less than or equal to lambda. Okay, so of course this indicator function, this is some good notation, but it's going to be a little bit more convenient just to have this as a function, just rather than writing indicator function all the time. I'm going to call this chi sub lambda of Fourier variable psi. And now I'm going to define pi L for low. We're talking at low frequencies. This is a low frequency cutoff. If I'm going to write low frequency cutoff, is now the Fourier multiplier corresponding to this Fourier symbol here. Okay, and then so this is i.e. pi L acting on function v is, okay, I go into Fourier space, I multiply by chi sub lambda, and then I Fourier transform back. Okay, and so therefore you can see that this returns the frequencies less than or equal to lambda. Right, it's a sharp frequency cutoff. I chop off, ditch all the all the frequencies greater than or equal to lambda, and keep the ones less than or equal to lambda. And now I'm going to define pi high or pi h as just I minus pi L, which is then actually the Fourier multiplier with symbol 1 minus chi sub lambda. And this is going to, you see, this returns frequencies greater than or equal to lambda. So now, when I'm using the Fourier transform, I like to have things in L2, right? And as we saw, the Helmholtz solution, so in L2 of RD, right? I'm using the Fourier transform in RD. And what is nice to have things in L2 of RD, right? Because Fourier transform acts nicely on L2 functions. Now, my Helmholtz solution isn't in L2 of the whole space. We talked about that in the first lecture. But this splitting, I'm free to choose some arbitrary ball of radius r and split the solution there. So what I'm going to do is I'm going to choose a compactly supported phi in RD with values between 0 and 1, such that phi is identically 1 on the ball of radius r, and say the support of phi is contained in the ball of radius 2r. And now my UA is going to be pi L, the low frequency cutoff applied to phi U, and restricted this to the ball of radius r. And UH2 is going to be the high frequency cutoff applied to phi U, and again restricted this to the ball of radius r. Okay, so we have then that on the ball of radius r, U A plus UH2 equals phi U, which equals U because of this support property here, right? And where of course I'm using the fact that pi L plus pi H equals 1 by this definition. Okay, so as claimed earlier, UH2 is going to be the sort of high frequency components, the components with frequency greater than or equal to lambda. Okay, and this is with our scaled Fourier variable. So if we're using our unscaled Fourier transform, this would be the components of frequencies greater than or equal to lambda times k, if we're using the thing unscaled with k. And then UA is going to be the low frequency cutoff applied to phi U. So this is the frequencies less than or equal to lambda in the scaled variable, where if you converted it back to your regular Fourier transform, it will be less than or equal to lambda times k. Right, so now I've defined what these functions are. Now I need to prove the bound on UA, the bound on UH2. I'm going to make some general remarks, and then we're done. So exactly, yeah, we've got one slide bound on UA to come, one slide bound UH2, then one slide of general remarks, and then that's it. Right. Yeah. So sorry. Is that a question?
This is a question. Is the R
good?
Is the R going to vary eventually?
So R is completely arbitrary, right? So yeah. So R is somehow we get to choose R, right? So we want it to contain. We're given an F with compact support. We solve our Helmholtz equation. We then restrict. Well, we're allowed to restrict to a ball of radius r for any r as long as that ball contains the support of F. Okay. So yeah. So
depending on what you're interested in, like what part of the solution you actually are interested in.
I'm sorry, I can't hear that.
So the R depends on your application. What part of the solution you're interested in probing.
Yeah. So exactly. So going back to the sort of finite element world, you choose then R big enough to contain the bit of the place in space where you want to know what the solution is.
Yeah.
Okay, good. Right, this is it. What the first we're going to prove for the bound on UA, right? The low frequency part. And the one line, so if right now my partner called me and said, Ewan, your son's nappy needs changing. He's, there's been a poo explosion, I can't deal with it. And I had to rush off and change this nappy. I would leave you with the sentence. I would say a function with compactly supported Fourier transform is analytic. And then I would and then see again. So and I wrote this a little bit roughly as if I were actually having to rush out and go and change a nappy. And then I trust, having told you this, I trust that if I came back then, 5 minutes later, having changed the nappy, you folks would have worked out and proved this bound on UA yourself. But luckily, at least I got my headphones on. So if my partner is telling me this, then I can't actually hear her. So I will stick around and prove this bound on UA. Right, so this bound on UA involves these weighted derivatives. So K inverse D, alpha, UA, this is L2, the ball of radius R. In fact, wouldn't it be good if I cut and pasted what this bound we're heading towards is and stuck it at the bottom of the page? Copy. Paste. Okay, so this is the bound we're heading for. Okay, I'll leave that highlighting there. Okay, this is what we want to get to. So this is equal to. Okay, so the first thing I'm going to do is I stick in my definition of UA, right? So UA is the low frequency cutoff pi L applied to phi U. And this is on L2 of BR. And now I want to move to the full space RD because I want to use my Fourier transform there. So then this is certainly less than or equal to the norm of just this exact function, but now on L2 of the whole space. L2 of RD. Okay, now I use Plaucherel's theorem, and I can, so that then this norm is equal to K over 2 pi to the D times then the norm of the Fourier transform of this thing, right? So I've got my derivative rule that tells me I'm going to get a, okay, I'm going to abuse notation here and actually write this variable that's getting, that's in this, so I've got this L2 norm. It's got it's got an integration variable. I'm going to abuse notation and actually write that variable in the norm. So this then, this turns into this. Then the Fourier transform of pi L, well, this is just this indicator function cutoff times then the Fourier transform of phi U variable psi L2 of RD. Okay, this is then by Plaucherel, not Parsifal. And now, so this chi sub lambda is just the indicator function cutting things off for frequencies at frequency lambda. So this quantity here is then less than or equal to lambda. So the modulus in that quantity is less than or equal to lambda to the mod alpha, because I'm cutting off to these frequencies less than or equal to lambda. So this is then less than or equal to, okay, I've got my K to the over 2 pi to the power D, lambda to the mod alpha. Now the Fourier transform of phi U. In fact, now I don't need to write this variable. Now I just use Parseval again, lambda to the alpha, phi U, L2 RD. And now I can use, so let's actually, okay, let's do one more step. This is less than or equal to lambda to the alpha. Now phi, the support of phi, for phi was 1 on this ball of radius R, and it was 0 outside the ball of radius 2R, right? So this is then less than or equal to U L2, the ball of radius 2R. And now I use this bound, this a priori bound on U, that again, you can get with integration by parts. just to say this is then less than or equal to, okay, lambda to the alpha, the constant k times r FL2. Right, this is their a priori bound. Okay, and we see exactly that we've then proved. Okay, this, in fact, let's go. This is this, and this. Okay, right, so then the required bound holds with C3 equals lambda, and this C2 equals the constant C. Right, so we proved this bound on UA, that's the low frequency part of U. And yeah, like I said, it's coming from the fact that if I have a compactly supported Fourier transform, this function is then an analytic. Okay, that's it. We've proved, okay, we've done step one, right? Proved the bound on UA. I'm going to take another drink of water here. It's a bit hot here. Kirill, when are you coming back to the UK? Because you got this, what you got the workshopy thing next week, right?
Yeah, that's right. We have a workshop next week. Okay,
it's good because and what's the temperature like where you are now?
It's something like 30, 32 and
32
and high humidity.
Okay. So we're not quite there yet, but we're going to get there. So in Bath, it's going to be 36 on Monday.
Right. Okay. And how about humidity?
I don't know.
It's it was 36 when I went to Dubrovnik in June.
Okay.
And it felt better than easier than here because it was dry.
Okay. No. Yeah. Okay. No.
Suffering. Yes, I know. I know you're.
Yeah. No. I wasn't trying to turn this into a sort of battle of who's in the most difficult conditions. I was more just seeking to have a 1 minute kind of banter whilst everyone relaxes for 1 minute before going and doing the next bit of the proof. But I couldn't hear that, but I'm going to ignore it. Okay, because that's it. The small talk allocation has been used up now. Right. You've all had a little rest. Proof of the bound on UH2. Okay, so now, good. See, look, I'm getting excited. Because now what Stephen said, right, about it's going to be some good property of the principal symbol, this is going to come in here and help us. Okay, and so actually, okay, let me do what I did last time, which is copy the bound I'm trying to prove. Copy and stick it at the bottom of the page. Come on, iPad. I mean, sorry. I copied you, right? There we go, paste. Okay, so this is the bound we want to prove. Let's stick it up here. Right. So the norm of UH2 in H2, the H2 norm. This, okay, what's the definition of UH2? It's the high frequency cutoff, pi high, pi h, applied to phi times U. And this is then, okay, it's less than or equal to the norm of pi h phi u on the whole in H2K on the whole of RD. Now, I use my definition of pi, so pi high is this Fourier multiplier, pi h. So it's 1 minus chi sub mu K inverse D applied to phi u. Okay, so all I've done now is just written out what the definition of this pi h is. Let me highlight that. Okay, now we use what Stephen was saying, which is that if, okay, lambda is greater than or equal to some lambda naught greater than 1, then there exists a constant c, depending on this lambda naught, greater than 0, such that mod psi squared minus 1, the modulus of this, is bounded below by some constant c, then times this angle bracket, sorry, constant c, then times this angle bracket psi, for mod psi greater than or equal to lambda. Okay, and this thing here is the principal symbol in this, using the weighted Fourier transform of my Helmholtz operator. Okay, so this is really the heart of it. I mean, of course, it's simple, but it's the heart of it, right? It's saying that if, essentially, if my modulus of psi is greater than 1, okay, a little bit greater than or equal to lambda greater than 1, then I can bound this thing below by this is then 1 plus mod psi squared. Okay. And now I do the mathematician's favorite trick. So my director of studies as an undergrad said to us all, a mathematician is someone who knows that 0 is 1 minus 1. Yes. And here we're going to know that 1 is x over x, right?
Add and subtract.
Exactly, add and subtract. But so here we're going to multiply and divide. Because you see 1 minus chi mu, okay, like this in the Fourier world restricts to frequencies greater than lambda, right? It restricts to mod psi greater than lambda. And so therefore this P, the Fourier multiplier, P K inverse D, oops. I can put this Fourier multiplier P K inverse D in here, right? Which is just the Helmholtz operator. Okay, so let's be more precise about this. The claim here is that, so the claim here is that 1 minus chi sub mu of psi over P of psi, this is a Fourier symbol, and in fact I'm claiming it's a Fourier symbol of -2. Okay, because so I'm divided by this P. This P could be 0 if psi were 1, but the high frequency cutoff is cutting off. It's getting rid of these frequencies where psi is less than or equal to lambda. So this thing is legal, and it goes like 1 over psi squared at infinity. So that's this Fourier symbol -2. Okay. So and now we have this mapping property, right? I said if you have this Fourier symbol of -2, then the Fourier multiplier has this nice mapping property between Sobolev spaces. So this is then okay. I'm going to go to the left-hand side of the board. This is less than some constant, then times P K inverse D acting on phi u, and now I go down from H2 to L2, right? Because precisely of this, because this -2 here, I go from H2 just to H0, i.e. L2. Right, and now I'm kind of so remember this P of K inverse D is the Helmholtz operator, right? So I've effectively got Helmholtz operator on U, that's kind of F, right? So I'm almost done, right? I'm almost got the right hand side being F. The only difference is I have this phi here, right? So I need to do something about that, but it's not going to be difficult. So this is okay, constant. So now this is phi times f plus then the commutator of the Helmholtz operator acting on phi, commutator of that with phi acting on u. This is L2 of BR, sorry, L2 of RD. And then just by hand, you can work this out. It's got some first derivatives. So let's say this is less than or equal to constant times f L2 RD, because I assumed that phi was less than or equal to 1, plus then I get 1 over kr, then a first derivative of u from this commutator. And this is on the ball of radius 2r, because that's where phi and therefore its gradient are supported. Okay, so there's sort of one step of algebra here that I've omitted. And then this is now, again, I use my a priori bound on the solution that says the norm of u in all these weighted spaces is bounded by kr times the data. Okay, and so then that kr is cancelled by this, and I get then less than or equal to c tilde f of L2, which is exactly, which was what was wanted. This is this here. Okay, and but what I want to emphasize, okay, so there was this fiddling around here with this commutator at the end, but the heart of it was putting in, was multiplying and dividing by the Helmholtz operator, and dividing by this Fourier. So rather, sorry, this should be a sort of, so I should be more precise here. This is more kind of, so sorry, that's okay. But the heart of it was the fact that this Fourier multiplier here, 1 minus chi mu over p, was well defined, because the symbol of the Helmholtz operator was, so I want to say, I'm going to say the word elliptic on high frequencies. Okay. Kirill, are you with me?
Yeah, sorry, I just missed your explanation for the equality, the first equality in the last line.
Here, right?
Yeah. So what?
So okay, so that's okay. So this p, so let's do it. Okay, so this p is minus this p is the Helmholtz operator. Yeah. So I got the Helmholtz operator acting on phi u, and so that's then, so let's say, so minus k squared Laplacian minus 1 acting on phi u. This is phi minus k squared minus k to the minus 2 Laplacian minus 1 u, plus then the commutator.
Okay.
Yeah.
Okay. I see. So you moved it over, you pushed it through onto u.
Yeah.
Okay. And then we gave you f, and then you had something nicely behaved on u.
Yeah, exactly. This gave me the f.
Yeah.
And then this, this is nicely behaved, because I get this kind of I get this inverse power of k. Okay, so we now finished the proof of the theorem. We proved the bound on UA. That's the analytic part that comes from the low frequencies. We proved the bound on UH2. That's the H2 part with 1 power better k dependence than the solution, and that's coming from the high frequencies. So I want to now give you just one more slide, and then I'm done. So I could rewrite. So this fact we did here, this sort of multiplying and dividing by this p Fourier multiplier, I can rewrite what we did there a bit more generally. Okay, so I'm going to write that as I'm going to call it a theorem. This is again a simple theorem, but important nonetheless. So what we really did was we said, suppose that I have a Fourier symbol A and a Fourier symbol B, and there exists a constant C greater than 0, such that B is bounded below by, okay, let's make this by the C times psi to its order, right? So B is a Fourier symbol of order MB, and then this symbol B is bounded below by the angle bracket psi to that order for psi on the support of A. Okay, so I claim that's the setup we had on the previous slide with, so we had B was equal to this, look at it, we had B of psi was equal to this P of psi, this mod psi squared minus 1, and this was bounded below by some constant angle bracket psi squared, basically on psi greater than or equal to lambda greater than 1, right? That's this fact we use. So then the Fourier multiplier so A can be written as Q times B, so I can factor out B somehow of A, where this Q is a Fourier symbol of order MA minus MB, and such that Q of psi is just A of psi over B of psi, right? Because of this fact that B is bounded below on the support of A means that Q makes sense, right? This is like, means Q makes sense. Right? And so it and it's exactly the fact that for us on the previous slide, A was this 1 minus, A was the cutoff to high frequencies, you know, and somehow A over this Helmholtz symbol made sense, right? This was so Stephen, do you agree that's what we used on the previous slide?
I agree that this is correct.
Good. And so I'm going to write here that I'm going to write here that minus k squared Laplacian minus 1 is, oh my God, what happened there? Look at it. Just at the denouement of the talk, my iPad decided to freak out. Is elliptic for mod psi greater than 1. But of course, we're using our Fourier transform with this parameter K inverse built in. So K inverse is a small parameter, and somehow, so actually, more precisely, I would say the Helmholtz operator is semi-classically elliptic. And this adjective semi-classical just means I'm weighting everything by the small parameter K inverse, right? I've got my Fourier transform weighted that way. I've got these Fourier multipliers weighted that way. So this is this sort of fact. So this is the one sentence summary somehow of why we could prove this nice bound on UH2. Okay. So what we've done is we've shown, okay, so we've proved this splitting result, that for this full space constant coefficient Helmholtz equation that Melik and Zauter proved in 2010. So and we've given a simpler proof than them. They somehow applied these frequency cutoffs to the data, and they had to then estimate a lot of Hankel and Bessel functions, and the proof was more complicated. So that's the sort of novelty of the stuff I presented you today. That's one novelty. But the second novelty is this proof I've just given you today generalizes or can be extended to much more general situations. Because how I got into this, thinking about these problems, was I wanted to prove the analog of this Mellink-Zauter splitting for the variable coefficient Helmholtz equation. Okay, and now this variable coefficient Helmholtz operator, so minus k to the minus 2, divergence of a grad minus, okay, n, some other variable coefficient, this is not a Fourier multiplier. Okay, unlike the constant coefficient Helmholtz equation, this variable coefficient creature is not a Fourier multiplier, but it is a pseudo-differential operator. And I'm going to use the adjective again, semi-classical, just to mean, again, it's a pseudo-differential operator where I'm basing everything on the Fourier transform weighted by this K inverse small parameter. Okay, and the generalization of this result here, this theorem here, so the generalization of this from Fourier multipliers to pseudo-differential operators is what's called the elliptic parametrics. So in fact, you know, so what happened is, so back just in 2020, Jared, David, and I, we wanted to prove this Mellink-Zauter splitting for these variable coefficient thing. We used pseudo-differential operators because, you know, these are great tools to study these variable coefficient problems, and we use semi-classical pseudo-differential operators because we've got this small parameter here. And then, you know, later, then actually, when giving these lectures in ETH Zurich at the end of last year, I realized how in the constant coefficient case, this proof just reduced to using Fourier multipliers and was kind of then quite nice and simple. Okay, so that's the end of this lecture series. Somehow, what do I hope you take away from it? Well, I hope you'll understand what the pollution effect is in this context of the finite element method, and I hope you have seen what this then proof that in this sort of simplest possible case, the HP finite element method doesn't suffer from this pollution effect. And then if you've never seen pseudo-differential operators before, somehow then this Fourier multiplier theory that we talked about today is then a sort of I hope can be a bridge to then understanding the pseudo-differential operator theory. And then finally, I want to say that actually, you know, this sort of simple fact, right? We saw that this Helmholtz operator is semi-classically elliptic on high frequencies. Somehow we've used it in this course to show that this HP finite element method doesn't suffer from the pollution effect. And also actually recently, Jeff Galkowski and I showed that the boundary element method, so when you use integral equations to solve the Helmholtz equation, the boundary integral method, boundary element method, doesn't suffer from the pollution effect. And this was more complicated because we're using integral equations, but actually that proof again boils down just to this simple fact that the Helmholtz operator is semi-classically elliptic on high frequencies. So even though what we did today was all this sort of simple Fourier transform stuff, you know, continuing to run with that idea allows you to prove these exciting results in numerical analysis. That's it. Thank you very much. I'm happy to answer questions.